whether we reach an efficient situation. You can think of efficiency as the size of the pie, and the goal being to maximize the size of the pie. And equity is about the distribution of the pie, how the pie is sliced among different people. That can vary, but first and foremost, economists would say we have to enlarge the pie, maximize the size of the pie as much as possible. Maybe the pie is too North American, so the size of the chapati. So by now you're all familiar with the Pareto principle. Here is a photograph of our new best friend, Wilfredo Pareto. So just to summarize, somebody's at the door. Allocation is Pareto efficient if you cannot make one person better off without harming another person in the process. This sounds very appealing. Unfortunately, as Professor Tranchal mentioned, it's not very practical. Because in most contexts, in most situations, that's not possible. We're going to distinguish between production efficiency and consumption efficiency. Production efficiency is when we cannot produce more output at the current cost given the current knowledge. And consumption efficiency is a situation where goods cannot be reallocated across people so that at least someone is better off and no one is harmed. And at least in the context of two people, which is the context we're going to start with, this is going to be relatively easy to spot. Those situations where we cannot improve the situation without harming someone. So we're going to start in a pure exchange economy, an economy where nothing is produced, the amount of goods available is fixed, and people start with an endowment, and the only thing that they can do is trade. And trade can be beneficial if it's voluntary. If I voluntarily trade, that means at the end of the trade I must be better off than before, otherwise I would not trade. So by definition, voluntary trade is optimal. So we're going to show that in a formal way, something that should be quite obvious, that the free trade is Pareto efficient. And if we have time, we can say something about how this theory basically extends not just between two individuals, but between countries. So that's why economists like to lower barriers to trade. And that's why there was so much fuss over the last few months over Donald Trump's tariff war. Maybe you've heard about it, yes. Hopefully.
Yes.
So it should be quite obvious that after all voluntary trades have occurred, have been exhausted, we cannot reallocate goods so as to make someone better off without harming somebody else. Otherwise, trade would not be exhausted, people would continue to trade voluntarily. Okay. So we are going to first demonstrate that trade between two people has this Pareto property of efficiency, and then show that the same property holds in a competitive market. So at first there are no prices. We're just going to assume that people barter, trade in the old ways without money, and then we're going to introduce prices, and therefore a market. The assumptions that we make in order to prove this fundamental result is going to speak to those people who have studied a little bit of microeconomics. So people maximize their utility, maximize their happiness. Okay, they're selfish. The happiness of others does not enter their utility function. So people just look after themselves. They're not altruistic. They have usual-ship indifference curves. So they have, let's say, standard preferences. How many people are familiar with convex indifference curves? You must have seen that in your economic sequence. One person. Most people are not familiar with so-called indifference curves, so I'm going to have to introduce that. That's fine. It's just the indifference curve basically connects every point that gives you the same amount of utility or happiness. Okay, so if 2 rotis and 1 chapatis give you the same utility as 3 chapatis and 1 roti, then those 2 points are going to be in the same curve. Non-satiation means that you always want more, which is a common assumption in economics. Okay, people never rest, they are never satiated, they will keep eating until the very end. And no interdependence means that my utility only depends on what I consume and not on somebody else's. So that rules out things like jealousy, where you consume something and suddenly that would make me worse off because I suddenly want it. That's a complexity that we're going to try to avoid. So these are very standard assumptions, although they may be framed in theoretical terms. So we start with endowments, so what people have at the beginning. And I'm going to introduce this through an example. There's going to be 2 individuals, Jane and Dennis, and we're going to assume that they are stranded in the wilds of Saskatchewan. Who knows what Saskatchewan is? One person. It's a province of Canada. It's a province in the middle of Canada. So it can be very cold in the winter and very hot in the summer. And they grow a lot of wheat there. Okay, so given that, they must either trade with each other or consume what they have on hand. Let's assume that collectively they have 50 cords of firewood to make fire and 80 candy bars, and they cannot produce any more. So that's the total endowment of this economy. And we're going to assume that Jane starts out with 30 cords of wood and 20 candy bars. So now I'm going to show you their endowments. Hopefully the computer will keep working. So this is their endowments using that concept of indifference curve. Okay, so there are 2 goods, which is nice for us because with 2 goods we can represent that on a nice diagram that we can picture. If we had more than 2 goods, we would go into higher dimensions that would be more difficult to picture. That's why economists love examples with 2 goods. And so observe these curves, the red curve and the blue curve. By definition, or I should say by construction, they connect all the dots that represent the same level of happiness. And as you can expect, the shape is such that if you have more firewood, you must have fewer candies in order to stay on the same indifference curve. Because if you have more of both, necessarily you're happier. So you cannot be on the same indifference curve if you have both of more goods. Does that make sense? Yes? I get an enthusiastic response. Okay, so but this is important because this is the first step. Okay, there's going to be an extra step afterwards. So you have to be comfortable with this representation of the economy. Okay, so UJ is the utility of Jane, and UD is the utility of Dennis. Okay, it represents a certain level of happiness. But there are infinitely many indifference curves representing infinitely many levels of happiness. There would be another indifference curve here that would represent a higher level of happiness, and another one here that would represent a lower level of happiness, infinitely many of those. Make sense?
Yes.
Yes, sir.
All right. So now the extra step is to combine combine those two diagrams to form something called an Edgeworth box. Okay? So what we're doing is that the diagram for Jane remains the same, but the diagram for Dennis has just been rotated and put on top of Jane's diagram to create a nice box. Okay? So this is the total endowment of the economy and the starting initial positions of each. And we call that endowment E. Okay, so this doesn't change for Jane. And if you put your head upside down, you will see that this is Dennis just as before. We're just putting Dennis's diagram on top of Jane's. Okay, perfect. So maybe you've seen this before.
Yes.
So you have, okay. Who hasn't? Some people have not seen, okay. So here we are. We have those two individuals. They're stranded, they cannot produce more. All they can do is trade. Immediately, if you understand the concept of indifference curve and what it represents, the fact that everywhere to the right of the red curve represents allocations that are better for Jane, and everywhere on the left of the green curve represents allocations that are better for Dennis, immediately you should see that E is not an optimal point. Why? Because in this lens here, all the points here give a higher utility to each of them. That means that E cannot be the end of the story. We would like to trade to get an allocation that makes each of them better off. And that's what's going to happen. Okay? So this area B is the only one where each of them is strictly better off. Make sense?
Yes.
Okay. So here are difference in difference curves. And there are infinitely many of them. There is a reason why those three are drawn that way. We could draw many more, but three is enough to get the idea. Why are they drawn like this? To show you a specific point, which is the tangency point, where both curves just touch each other. If they touch each other, that means that they cannot be both better off starting from that point. Okay, so if you imagine that the endowment is at point C as opposed to point E, then, well, Jane wants to be to the right of C, and Dennis wants to be to the left of C, and that's impossible. It's impossible to satisfy both of them. So at C, they will stop trading, and that will be the end of the story. Okay? And of course, C is just one particular point, but we can look at the same point F here. It has the same property where nobody wants to trade further. And B, the same thing. And you will be able to do that for all the points that basically are tangent between the two curves. And the next step is going to be to connect all those tangency points. Okay, so at F, will they make any further trade? No. So we started with E. E was not optimal, but if they reach F, and you can see that F means that Jane gets 20 more candies and 10 fewer cords of wood, and Dennis gets 10 extra cords of wood and 20 fewer candies, then this allocation F is optimal in the sense that nobody wants to change that new status quo. Now, I'm going to introduce something that some of you are familiar with, other people may not be familiar with. It's the concept of marginal rate of substitution, and that is the slope of the indifference curve. Okay. So the slope of the indifference curve represents how much they're willing to trade one good for another while staying on the same level of happiness. So each of them has a marginal rate of substitution. J stands for Jane and D stands for Dennis. So how to interpret this marginal rate of substitution? Jane's marginal rate of substitution is -1/2. What does that mean? At point F, she's willing to trade 1 quart of wood for 2 candy bars. Dennis, same thing. And because it's tangent, it has to be the same. Okay? The marginal rate of substitution is the slope of the indifference, the slope at the indifference curve. And because the two indifference curves touch each other, the slope has to be the same. And so, if they both want to trade wood for candy at the same rate, they can't agree on further trades. If you took another point, say the initial point E, so what they started with, remember that their indifference curves were not tangent at that point. Okay? And at that point, it can be shown that the marginal rate of substitution was -1/3 for Dennis and -2 for Jane. What did that mean? That meant that Dennis was willing to give 1 quart of wood for 3 more candy bars, or equivalently to sacrifice 3 candy bars for 1 more quart of wood. In that situation, if Dennis offers Jane 3 candy bars for 1 quart of wood, which is the maximum that she's willing to do, Jane will accept. She's willing to trade. She's willing to give up 1 quart of wood for just half a candy bar. So that trade makes Jane strictly better off. Okay? So trade occurs, which means that the initial position was not optimal. We reach an optimal point where no further trades are possible. That means nobody can be made better off without making somebody else worse. So, long story short, trades are possible where indifference curves intersect because marginal rates of substitution are unequal. So we can say 4 equivalent statements about bundle F. The indifference curve of the two parties are tangent at F. The parties' marginal rates of substitution are equal at F. No further mutually beneficial trades are possible at F. And the allocation at F is Pareto efficient. All 4 statements convey the same substance, the same meaning. Does that make sense? Okay, so as I promised, we were going to connect all those points where the indifference curves are just touching each other, where the marginal rates of substitution are the same for each. And we call that the contract curve. So we connect all those points of tangency, and we just draw that curve, and it looks like this. So I only put 3 examples, but because there are infinitely many indifference curves, there are infinitely many points of tangency, and all that we do here is to connect them. So all those points are representing efficient allocations in the Pareto sense. But immediately, you should realize that they are not all equitable. Because Jane having everything, for example, is an efficient allocation. Dennis having everything and Jane nothing is another efficient allocation. Nobody would say that they are equitable. So we have a sense that equity lies somewhere in the middle, but we cannot really pin down a particular point that is the maximum of equity. So that's the problem. It's much easier to represent efficiency than equity. And that's also why efficiency is a weak concept, because it represents too many situations, some of which are desirable, some of which are not. And to make things worse, I think most people would agree that in the most extreme cases where we reach an efficiency point, we would be willing to sacrifice a bit of that efficiency for the sake of redistribution, for the sake of equity. Okay. So what bundle will they choose between, say, B and C on that contract curve? Well, we don't know. It depends. So remember that B and C represents two extremes within the length of possible exchanges. So the segment between B and C is where the final allocation will be starting from point E, which is not represented here. You may remember what point E was. But economics doesn't say where people are going to end up because it depends on who is better at bargaining. Okay, so that was for exchange without prices. Now we're going to introduce prices. Because in the real world, most trading occurs without bargaining. Okay. So if we know the exact trading process that people use, we can apply that process to determine the final allocation. What we're interested in is the final allocation. So we're going to examine the competitive trading process because that involves prices, and if we find that trading with prices leads us to an efficient allocation, well, we will have to say something quite valuable about the importance of having prices in the economy, and particularly prices that convey meaning. So prices, we take that as granted in our economy, but the signaling value of prices is something phenomenal. Okay? It simplifies all our transactions to the point that we don't even appreciate it anymore. But just imagine what we would do if we didn't have prices to compare things. We would have to make infinitely many comparisons and calculations all the time. And we would be consumed by that. So it's a magnificent process, the invention of prices. So we're going to see all the benefits of a competitive equilibrium, an equilibrium that has prices embedded in it. And in that framework, we're going to show those two fundamental results, which are the first theorem of welfare economics, which is that the competitive equilibrium is efficient. We've already seen that the bartering equilibrium is efficient. We're going to see the same thing in the context of a competitive equilibrium. And something a bit more subtle, more difficult to prove, which is that any efficient allocation can be achieved by competition. That's the more subtle statement. So let's do this. First of all, of course, these theorems proceed from axioms, so we have to satisfy a certain number of assumptions, which are that everyone knows their preferences, and of all the traders as well. There are no transaction costs, so no leaky bucket. The indifference curves have their usual shapes. And if all of that is verified, then we can get those fundamental results, which are, again, noble price quality results. So they're not trivial. They're not trivial when you generalize the economy to an arbitrary number of individuals and an arbitrary number of goods. It's much simpler when you have only two individuals and two goods, and I'm happy to just show you that today. Okay, so returning to the previous example, let's assume now that Jane and Dennis are price takers. You and I are price takers when we go to the store. We don't create the prices, we take them as they are. Okay, so this is a very simplified economy with only two goods, so each person needs to consider only the relative price of the two goods when deciding whether to trade. And therefore we can normalize one of those goods to be one. We can call that the numeraire good. Okay? What is the numeraire good in the Indian economy? It's your 1 rupee coin. Everything else is compared to that 1 rupee coin. That's the numeraire. So we have only two goods, and one can be called 1, and the other is the relative price of that good to the one called 1. And this can be generalized to n prices. This is called Walras's law. When you have n goods, there are only n minus 1 prices. Okay. So with Jane and Dennis as price takers, we're going to assume that the price of the candy bar is 1, so without loss of generality, and the price of a cord of wood is twice as much, so 2. And so the relative price, PC over PW, price of candy over price of wood, is 1/2. So we can model the purchase decision of Jane and Dennis using an Edgeworth box. So this is something that if you've taken some microeconomics, you're familiar with. The slope of the price line here is the budget constraint, and people are trying to maximize their utility with the condition that they cannot go above their budget constraint. They can spend all their money, but not more. And given that the assumptions that we've made, that people always want more, that the non-satiation principle, you can be sure that people want to be on their budget constraint. Any point below would mean that they haven't spent all their money. So we have two conditions. They want to be on their budget line, they want to spend all their money, and they want to be on the highest possible indifference curve, because that represents levels of happiness. So if you put those two together, you realize that the optimal thing will be to be exactly on the point of tangency between the budget constraint, the price line, and the indifference curves. So that would be point F here. So that price line leads to a competitive equilibrium. If we start from point E and we trade according to those two prices, I mean, actually, not those two prices, that one price, because there's only one price when you have two goods. Okay. So with that one price, if you keep trading starting from point E, you're going to reach the allocation F. And that's the miracle of the competitive exchange economy. Okay. So to recap, the price line shows all of the possible combinations Jane can get from trading, given her endowment. And Jane will choose the bundle that maximizes utility. And we see that Jane and everyone like her wants to get 20 candy bars and 10 cords of wood, starting from her endowment point. Given that, the quantity of wood sold equals the quantity bought, and the quantity of candy demanded equals the quantity supplied. And that's the end of the story. We can also look at another situation, a situation which also goes through point E, which is the initial allocation, but would not lead to a competitive equilibrium. So the slope here is different. And so when people maximize their utility, given that new price line, what do we end up? We end up with two tangency conditions, one at J for Jane and one at D for Dennis. And you can see that J and D are different points. They represent the best that they want to achieve, but those two points are incompatible. Okay? Why are they incompatible? Well, you can see that directly from the graph. There is a total of 80 cords. There are 50 cords of wood in this economy. Okay, a total of 50 cords of wood. So when they make any exchange, it cannot exceed the total endowment of the economy. So at J, Jane wants 20 cords of wood, and at D, Dennis wants 32 cords of wood. Okay, so 22 plus 32, 54. That exceeds the total amount of wood available in the economy. So we know that this price level is not going to lead to an equilibrium. And same thing for the candy bars. Dennis wants how many candy bars? 43, and Jane wants 30, so that means 73. So that means not all of the candy bars in the economy are going to be exchanged. We want to exchange, we want the total amount of candy bars to be 80, and the total that they want to exchange here would be less than that. So there's something wrong, obviously. Too much wood, too few candies, that the prices are not correct. So in the background, there's going to be a hidden auctioneer that's going to adjust the price so that they go back to this situation that I initially showed you. Okay. So this is the non-optimal price. If the price of wood fell to 1.33, Jane would want bundle J, and Dennis would want bundle D, and we've seen that this particular price does not lead to a competitive equilibrium because the quantity supplied will not equal the quantity demanded for both wood and candy. Does that make sense?
Yeah.
Okay, so we're now in a position to say something about the efficiency of competition. In a competitive equilibrium, so an equilibrium with prices, where people are price takers, the indifference curves of both types of consumers are tangent at the same bundle on the price line. Okay, and we can write this mathematically. The marginal rate of substitution, remember we defined that as the tangent of the indifference curve. There are infinitely many indifference curves. As you move along the indifference curve, there are infinitely many tangents. But there is only one point that satisfies this equation where the marginal rate of substitution of Jane is equal to the marginal rate of substitution of Dennis and is equal to minus the ratio of prices. That satisfies the condition for a competitive equilibrium. And that is the first theorem of welfare economics. Okay, that's pretty neat. In other words, any competitive equilibrium is Pareto efficient, which is probably something that you would have suspected. If it's an equilibrium, that means it's a stable point. I mean, that's almost tautological. It's the definition of an equilibrium. Okay. So that means that people do not want to move away from it. So if they don't want to voluntarily move away from it, it must be efficient. You cannot move away from it without making somebody worse off. If those two people were better off, they would change, and that means that it would not be an equilibrium. It would not be a stable situation. Okay, so this is our fundamental result. And once again, the beauty of it is that it can be generalized when you have an arbitrary number of individuals, an arbitrary number of goods, and of course, an arbitrary number of prices, minus one. Does that make sense?
Yeah.
So we can reformulate given that all producers and consumers act as perfect competitors, we haven't seen producers yet, that will be introduced later. No one has any market power. A market exists for each and every commodity, which is not always the case. So this is the case of market failure, which we're going to see at the end. The first fundamental theorem of welfare states that a Pareto-efficient allocation of resources emerge, and a competitive economy automatically allocates resources efficiently without any need for centralized direction. This is a very powerful result because throughout the 20th century, hopefully not this century, but throughout the 20th century, a lot of states experimented with centralization and setting prices from the top, deciding which goods should have a certain price. So, in a capitalist economy, when a good is scarce, its price goes up until only those people who can afford it get it. In a centralized economy, where this theorem does not apply because somebody decides what the price is, as opposed to letting market forces run their magic, what happens? Well, you could see that in the former Soviet Union. You would see lineups. Okay, so a good could be cheap. The only problem is it's unavailable. So you cannot have a government deciding on the prices of the that will be tolerated in the economy, and obviously the government, if it's supposedly benevolent, wants to have all the goods available so that everybody can afford the same. Well, if you try that, you're going to have shortages everywhere. So it may sound like a very simple result, and this result has been known for maybe, in this version that I just demonstrated, probably at least a century. But that doesn't mean that everybody listened. Okay, so the fact that something is known and commonsensical doesn't imply that the people at the top will just abide by it. But I'm going too much into politics here. So let's move to the second theorem of welfare economics, and after that we'll have a pause, we'll have a break. So how to obtain an efficient allocation using competition as a mechanism. Okay. So of the many possible efficient allocations, governments may wish to choose one. Why is that? Because we've seen that not all efficient allocations are equitable. So maybe out of a sense of equity, a particular government wants to pick a certain allocation. Hopefully, it will pick that allocation on the contract curve, because we want to have both efficiency and whatever we believe is equitable. If we're not efficient, that means that we're somehow wasting something, some resources. So we want to stay on the contract curve. But we may not be able to start from the contract curve itself. Okay? So the government cannot just magically decide that this is the optimal allocation in the economy, and therefore we're going to decide who gets what, and hands off, it's the optimal thing to do. Nobody else wants to trade further. We have exhausted all potential for gains. The government cannot decide that. The government doesn't have that information. But the government could, in theory, decide on a certain allocation, and the question is, would that allocation, if you let people trade from that allocation, can it lead to the point that the government wants, which is an efficient one, but also an equitable one? So as we have seen, the competitive equilibrium depends on the initial distribution of wealth. Okay, so at point E, people are just going to move to point F. And so that's the result that I would like you to intuitively get, is that suppose that F is considered the optimal allocation in the economy, but the government cannot directly impose F on people. But suppose that for some reason it has the ability to choose an initial allocation that lies on the contract curve somewhere, such as point E, for example. Then all that the government has to do is to leave the economy at point E and then take a seat, take a step back, hold their hands, do nothing, and let people trade. And people from point E will naturally move towards point F. That's the spirit of the second theorem of welfare. If you cannot attain F directly, you can do it indirectly, starting from any point on the price line. Okay, so the competitive equilibrium F will result when the initial endowment is E or F. At F, it's trivial. In E, through competitive exchange, people will reach point F. And that's true for any bundle, any initial allocation on the price line. So obviously a Pareto efficient bundle X can be obtained as a competitive equilibrium if the initial endowment is X. That means we haven't changed anything. That's not a very interesting statement. The interesting statement is that the allocation can also be obtained if the endowment lies on a price line through X, where the slope of that line equals the marginal rate of substitution of the indifference curves tangent at X, which is the very formal way of saying the same thing that I said a few minutes ago. That is actually the second theorem of welfare economics. Any Pareto efficient equilibrium can be obtained by competition given an appropriate endowment. And that's a profound result. So, the second fundamental theory of welfare economics, the second fundamental theorem, states that society can attain any Pareto efficient allocation of resources, one that is more equitable, by making a suitable assignment of initial endowments and then letting people freely trade with each other. So it's an optimistic result in the sense that equity can be achieved without inhibiting efficiency. We will still be on the contract curve, we will still be efficient, and we will attain a particular point that the government wishes. Let's see if we should be pausing now. Okay. Well, we could do a little more before the break. So far, we started with bartering, and then we introduced prices, but people were not producing anything. In particular, people could not transform one good into another. So now we're going to introduce production in the economy and see whether our results still hold. So, as usual in economics, we start simple and we add baby steps. So, the notion of comparative advantage. Assume that Jane and Dennis can produce firewood and candy bars using their own labor. Jane can produce 3 candy bars or 6 cords of firewood in a day. She can spend a fraction of her day alpha making candy bars and 1 minus alpha making firewood. So she can make 3 times alpha candy bars and 6 times 1 minus alpha cords of firewood per day, maximum. Suppose that I vary alpha between 0 and 1. It's a proportion, it's a percentage, so I'm allowed to do that. We can draw what is called her production possibility frontier, the maximum that can be attained within this economy. So, if Jane works all day using the best available technology, she achieves efficiency in production. If she stays on that curve, so that means there is nothing idle in this economy, she just works. work-life balance, just work. And so she achieves efficiency in production along the production possibility frontier. And the J superscript means Jane. So that's all that can be done in this economy. That's for Jane. What about Dennis? Okay, before that, the slope of the production possibility frontier is called the marginal rate of transformation. We've seen before the marginal rate of substitution. That was for indifference curves. Now, the MRT, the marginal rate of transformation, is the slope of the production possibility frontier. If I have only one individual, the slope of that line is trivial. Okay? It's the same as the line itself. But we're going to see this is going to change. So slope -2. What about Dennis? To make things interesting, she must have other skills. Okay? So she will be able to also produce cords of wood and candy bars, but at different rates. And so just imagine that this is her production possibility frontier. So obviously, Dennis is more gifted at producing candy bars, and Jane is more gifted at producing wood. Okay, so they have different technologies. This is the same theory of comparative advantages, by the way, that prescribes that countries should specialize where they have a comparative advantage, not an absolute advantage. If we have time, we'll get into that. All right, so you probably can see what's coming next, because when I presented two separate graphs for Jane and Dennis before, what we did before was to combine them, and unsurprisingly, we're also going to combine those two graphs. Okay. So the marginal rate of transformation, what is the interpretation of it? It shows how much it costs to produce one good in terms of the foregone production of the other good. Okay? The production of one good has an opportunity cost in terms of the foregone production of the other good. Opportunity cost is one of the fundamental concepts of economics. Makes sense? So we say that someone has the ability to produce a good at a lower opportunity cost than someone else. That person has a comparative advantage in producing that good. So we already mentioned that. Dennis's marginal rate of transformation is -1/2. She has a comparative advantage in producing candy, and Jane has a comparative advantage in producing wood. So now we're going to combine their production possibility frontier. That's the total that can be produced in the economy. Okay, so if they both produce wood, they can attain 9 cords. If they both produce candy bars, they can attain 9 candy bars. So what do we expect? We expect them to trade, and we expect them to specialize. Okay. So suppose Jane and Dennis like to consume wood and candy in equal quantities. If they don't trade, they each can consume 2 cords of wood and 2 candy bars. But they can do better. If they trade, they can collectively produce 6 units of each commodity and can subsequently consume 3 of each, and therefore making each strictly better off. So whenever people have different comparative advantages, we expect them to trade, and that will make them strictly better off. So what I showed here for 2 individuals can be extended to many. So I can add another person, call them Harvey, and add their production possibility frontier, and you can see that it adds another segment. So the curve is still very choppy, it's not smooth, but as you add more people and more people to the economy, each of them having a slightly different comparative advantage, eventually you're going to get a smooth curve with infinitely many people. Okay? So all the kinks are going to disappear. We are going to end up with a smooth curve that is concave to the origin. And so the MRT will decrease as we move up the production possibility frontier. Okay, so now the blue line is the production possibility frontier when you have many people with different comparative advantages. Let me stop here for how many minutes? Typically a break here is